Hello everyone, my name is Manuel José Lopez Morales and I am an early stage researcher in the Marie Curie project Team Up 5G at the Universidad Carlos III de Madrid. I am going to make a presentation of the paper titled A Survey about Deep Learning for Constellation Design in Communications. This is the outline of the presentation. I will first introduce the problem of constellation design. I will then talk about the main machine learning techniques in the literature. I will continue with the technique called end-to-end learning. I will give some examples of constellation design using end-to-end learning, and I will conclude. The structure of a communication system is the following. A transmitter sends a signal modulated according to a constellation diagram through a communication channel, and then the receiver is in charge of reconstructing the signal that has been distorted by the channel. For instance, here we have the constellation diagram of a QPSK signal, and here we have the received symbols of when they have passed through an AWGN channel. In order to design the constellation diagrams and the decision regions given the different channel types, we follow different design criteria. Can be the bit or symbol error rate, the energy efficiency, the peak to average power ratio, etc. There are three main families of machine learning techniques. These are supervised learning, unsupervised learning, and reinforcement learning. Supervised learning aims at inferring a relation between a dataset of input variables x and a set of output variables y by optimizing the function parameters theta. If the output y is discrete, this is 1, 2, 3 or A, B, C, D, the task is to classify, and if it is continuous, the task is to predict. In unsupervised learning, the dataset is not labeled. This is, no y is given. The aim is to infer the output y from the input x, usually with a latent variable that conditions the performance of the algorithm and that is chosen by the engineer. Basically, the aim is to extract patterns in data. Reinforcement learning is based on the use of a reward signal. The algorithm learns by experience. If it takes a good action, the reward is positive. If not, the reward is negative. The aim of the algorithm is to learn to find the best sequence of actions that collect the most reward. The components include an agent that acts according to a policy by observing rewards, and states of the environment, and an environment that generates a reward and changes its state with respect to actions. The last technique of machine learning I am going to talk about is deep learning. Deep learning is based on the use of neural networks. They aim to map a real input vector of size n to an output vector of size k by using a transfer function. It is composed of L layers. L uppercase layers, with each having a transfer function defined by the weights WL, BL, and the activation function sigma L, as we can see in this definition. The output. It is worth noting that the output of layer L-1 is in fact the input to layer L. Some things to consider about neural networks include the hyperparameters to tune, which are the number of layers, the learning rate, the types of activation functions, if and how to use dropout, regularization, early stop, avoid overfitting and underfitting. So basically, the difficulty in neural networks is not the mathematical notation, which is basically matrix algebra, but how to select, configure, and train the right neural network. In the classic approach of constellation design, the goal is to maximize the channel capacity. For this purpose, we need to define the marginal distribution of the transmitted elements and their probability. When the probability is uniform, the problem translates to the maximum likelihood optimization. The main limitation is that it needs to know the probability density function of the received symbol with respect to the transmitted symbol and the channel. Usually, the channel is unknown or it's very complicated to be mathematically tractable. In this context, end-to-end arises and is a concept that comes from autoencoders, which in fact aim to output the input to have the same output as the input by passing through a dimensionality reduction layer. This is very applicable in communication systems, which aim at outputting a reconstructed message S hat that in fact was inputted to the system as message S, passing through a dimensionality reduction layer, which is the channel. This approach, the end-to-end learning approach, eliminates the classical approach, complications and limitations, by substituting the modulator and the demodulator by neural networks and training them using a set of labeled data. The main limitation is in fact the access to a labeled dataset for the scenario where the neural networks must be trained. To perform the autoencoder training, we need to know the derivatives of the channel transfer function. Since this function can be very complicated or even unknown, we cannot get such derivatives. 3 solutions have been proposed in the literature to overcome this problem. The first solution consists of training using a simplified analytical channel model, and after that perform a receiver fine-tuning by training the receiver alone. So the first step is to simplify the channel transfer function to an analytical one, which unfortunately will not cover all hardware and channel inefficiencies, so the performance will be limited. Secondly, perform the autoencoder training. And third, substitute the analytical channel transfer function by a physical realistic channel and retrain the receiver alone by fixing the weights of the transmitter. The second solution aims to learn a generative channel model from data. Generative adversarial networks learn to mimic the distribution of any type of data. They are composed of a generator and a discriminator that compete with each other. The generator creates new data samples, y hat, using the latent variable set, and input x. The discriminator uses the input x, the real channel output y, and the generated output y hat, and is trained to decide whether y hat is fake or real. The training usually stops when the NAS equilibrium is achieved. This is, the discriminator is incapable of detecting whether the sample is fake or real. With this, we obtain a neural network implementation of the channel model that now allows for autoencoder backpropagation training. Nevertheless, it is difficult to model complex channels with a lot of randomness, so the usefulness of generative adversarial networks for autoencoder communication training is still under research. The third solution is to use a reinforcement learning technique in transmission. This is to train the transmitter by means of an RL agent. The minimum the agent needs to observe is a reward signal. In the case of communication systems, it can be the inverse of the bit error rate, the energy efficiency, the inverse of the peak to average power ratio, and many other possibilities. The observations of the environment can be provided, for instance, with the use of channel state information feedback. The receiver would be trained with backpropagation. So the approach would be, firstly, the weights of the transmitter and the receiver are set randomly. Then the receiver is trained with backpropagation by fixing the transmitter weights. Then the transmitter weights are trained with reinforcement learning by fixing the weights of the receiver. Then we repeat the receiver training, then the transmitter training, and so on in an iterative manner until some overall stop criteria is met. This approach benefits from the fact that it is transparent to the channel, but on the other hand, it consumes more computational resources and more time than the other two approaches. Here, I'm going to show the first example of the results obtained with these methods, when we train over an AWGN channel. It is interesting to observe that even though we have not taught the system to design constellations, when we tell it to use constellations of size 4, it creates a 4QPS, a 4PSK or a 4QAM. When we tell the system to use constant modulus constellations, it designs PSKs, and when we just tell the system to use a certain average energy, but we do not constrain to constant modulus, then it creates some kind of 16 irregular QAM. In the case of the multi-user AWGN channel, the autoencoder tries to orthogonalize the users in the constellation space. This is another example, which is the constellation design of NASA's tracking and data relay satellite system. In this system, the power amplifiers work in compression to maximize SNR and power efficiency. They use lower order or constant modulus constellations to cope with the severe nonlinear distortion caused by the amplifier. The autoencoder in this case can create an encoder network that learns a novel transmit waveform optimized for the nonlinear compression. The decoder network can yield a separable 32 symbol irregular QAM-like constellation. The last example I am going to talk about and that I'm showing you here is the bitwise and symbol-wise autoencoders for AWGN channel. When the optimization is done bitwise, the results are those shown on top, and when done symbol-wise are those shown on the bottom. In the bitwise case, from left to right, we go from least importance bit to greatest important bit. Therefore, one can check that the symbols are placed so that the ones differing in bits more on the right are at a higher distance, while those differing in bits more on the left are closer to each other. And this effect is more noticeable for lower SNRs. When increasing the SNR, the effect of the noise is lower, so the autoencoder resembles a classical regular QAM. For the symbol-wise case, the aim is to maximize the distance between symbols, with the SNR affecting only how the symbols are placed to minimize mean energy usage. So to conclude, we have talked about machine learning techniques, which are supervised learning, unsupervised learning, reinforcement learning, and deep learning. The end-to-end learning has three main approaches to deal with realistic channels. Analytical channel model plus receiver fine-tuning, which leads to suboptimal solutions. Learning a generative channel model and substitute it for the realistic channel so that then you can perform a full end-to-end training, a full autoencoder training, which is difficult and it's still under research for very complex channels. And the use of reinforcement learning in transmitter plus iterative training by using backpropagation in the receiver. This is the most promising technique, but it's also the most complex to implement. We think that end-to-end learning is going to be a key ingredient in the future generation of communication systems, since it's going to help to find optimal solutions for complex problems that engineers cannot solve right now with classical approaches. It is worth noting that the training overhead makes the design technique more interesting for deterministic or quasi-deterministic scenarios. Some research directions include further developing multi-user schemes optimization and cooperation, and developing proof of concepts for realistic deployment validation. The TMAP 5G project has received funding from the European Union's Horizon 2020 Research and Innovation Programme under the Marie Sklodowska-Curie project number 813391. Thank you very much for your attention.